Hello students. So this is lecture number 6 and we are still into chapter 2. Okay. So in the last lecture we learnt about the truss element. Truss element, and we found out that for uh, for a truss element, if there are forces, like for the bar we had this degree of freedom, so we have F1 and F2, and if the E A area length, then for the if the displacements are capital U1 and capital U2 are in the same direction, like aligning with the axis of the bar, then we have U, let's call it U dash, was U1 and U2, F dash was F1, F2, and the equation we had K dash U dash equal to F, where K dash was EA over L and then 1 minus 1 minus 1 1. Okay. So this was when the forces are aligned with the axis of the bar, the forces and displacement, right? So they are not oblique. Truss element, this is bar element, right? So this is the bar element. Now the truss element, where we have to say displacement is still displacement aligned with the x-axis. So there are two displacements per node basically, and the same bar we are writing it as displacement u1, u2, u3, u4. And we found out for this system also there is a stiffness K, and we derived that such that Ku equal to F, where K we derived in the last lecture, and U is equal to U1, U2, U3, U4, and then F we have F1, F2, F3 and F4. Today we are going to actually derive the same K but different method. Different method means we will use transformation matrix to do that, which is actually more mathematics than physics. Last time it was totally based on physics only, where we gave unit displacement and constraint in all other directions and find out the forces. Whatever the forces were there, we call them the stiffness, and from there we derive the whole stiffness matrix. Now given the stiffness for this one, is it possible to find out displacement for this one, right? So this system where all the displacement or forces are aligned with the bar, here actually here also all it can take forces only in the axial direction only, but our degree of freedom have changed. Instead of saying u1, we are now writing in terms of u1 and u2. Similarly, instead of saying u2, we are writing u3 and u4. Or Also we can, so instead of saying F1, we are saying we have F1, F2, and then F3 and F4. So let's see how we can do that. Okay. Now if you see here, the given the representation here and here, here our system is x axis is like this and y axis is like this. Here basically we can write like this also, right? So our axis system is rotating only, that's it. Okay, so the same bar like this we have, originally we have this x this way, y this way. You have rotated by x by theta angle with respect to the x axis, right? So let's see, let's to begin with, we will use the previous, let's use the previous case only, we will represent the previous case only where the forces and displacement are aligned with the axis only. However, we will use 4 degree of freedom. So meaning that we will say like this, we have okay, so we have at this node we have let's call it f dash, right? F dash, that is the force F dash 1, okay, and this direction also there will be a force, let's call it F2 dash, okay. In the other direction it has 0, okay. So basically in we have like this, in the vertical direction we have 0, and here also vertical direction we have 0. So in the 4 degree of freedom system, our forces becomes F1 dash 0, right, and then we have F2 dash 0, yeah, or you can relate this to this one, right? So we have F1 here, F2, capital F2 here. So basically we can also write, maybe we write like this. So we call it F dash 2 equal to 0. Let's call it F3 here. So this becomes F3, and this is F dash 4 equal to 0. We call like that. Okay, that will be okay. So F1 dash equal to F1 and F3 dash equal to F2, so that we can relate it with the previous system. Previous system means when we use the simple 1 degree of freedom per system per node. So here our x is aligned by with the axis of the bar only. Same thing I have drawn, but rotated basically. So I am using the same identities here, capital F1, capital F2, but writing in terms of 4 degree of freedom system. So here our force vector becomes something like this, right? So let's call it F dash, capital F dash. Okay. Now displacement accordingly also we can write, and displacement in the here we can write it as, we have this displacement, let's call it u1 dash equal to capital U1, basically u2 dash equal to 0, u3 dash equal to u2, and u4 dash equal to 0. Why u2? This is because we are relating with this one, right? So we have u1 here and u2 here, right? Okay, so that's what we are relating to that. Yeah. So this is in the 4 degree of freedom system, and we can write u dash equal to u1. So let's write here u dash equal to u1 dash 0 u2 dash u3 dash 0. All other values are 0, that's why I am writing. So this is nothing. Basically what I mean to say here, specifying 0 because f dash 2 equal to 0. F dash equal to f1 dash, f2 dash, f3 dash, f4 dash, but all others values, these two values are 0, and this equal to f1 dash equal to f1 only, capital F1. So you can write f1 0, f2 0, right? Similarly here in u, you will u1 0, u2 0 only. Yeah. Okay. And accordingly the k can also be split, since we know that the earlier from the earlier lectures we have relationship 1 minus 1 minus 1 1, and then we have f1 f2 sorry not f1 u1 u2. So u1 u2 equal to f1 f2, but this is in 2 degree of freedom system. We can write the same equation in 4 degree of freedom system, assuming x is aligned with the axis. Okay, so for if we have the so the just to this one is for 2 degree of freedom system. Actually what I mean is this is for 1 degree of freedom per node. Total element has only 2 degree of freedom system, and for this one this has total 4 degrees of freedom for the whole element. So 2 here and 2 here. So this one is the original representation, right? So the way we did in this case. Okay, so if we have force represented as this total 4 by 1 system, u by 4 by 1, so k has to be also 4 by 4 only, right? So let's say we have we had a system, which system EA over L 1 minus 1 minus 1 1, and then we had u1 u2 is equal to f1 f2. If we write the same thing as f1 0 f2 0, and here u as u1 0 u2 0, we can also write this, just modify, right, such that always u1 multiplies to 1 only, u2 multiplies to minus 1 only, and so on. That's how we can write. So basically how we can write? So we can say 1 here, then we have 0 minus 1 0, right? 1 u1 multiplies to 1 0 to 0, u2 multiplies to minus 1 0 to 0. right? We have like that. Similarly, the second one will be all zeros, because the second equation, this one, all zeros multiplied by all this becomes 0. So, we have this valid. Then we have the third one, like minus u1 plus u2. So, minus u1, so we have to write here minus 1 0 1 0 and then 0 0 0 0. So basically the original degree of freedom here was number. If you see, you can also look at the way we assemble, right? So how we did, the original system had like this was 1, this was 2, okay, that was 2 degree of freedom per node system, and the next degree of the current one, we have 1 here, 2 here, okay, then 3 here, 4 here. So you can see how it matching, this 1 and 1 matches, and then 3 and 2 matches, right? So that really means the first one here, in this one you can call it local system. Local 1 2 means 1 3. So 1 2 1 2, you have 1 3 1 3 1 3. So 1 3, whatever you have 4 point 1 3 1 3, you have point 1 2 3 4. There you are going to put those simply, right? The way you assemble, same thing you can apply here. In any way, what you got here is a same equation, this equation only, which are written assuming only 1 degree of freedom per node. Here you are writing exactly the same thing, but assuming there are 2 degree of freedom per node, and since there is nothing perpendicular to the axis of the bar, you are putting everything 0 corresponding to that. You are putting 0 here, 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 here. But the moment you rotate this one, this is not going to be the same thing. Why? Why? We can also look at basically. So let's draw the bar again like this, and then if we have a original force, it was F1, and now we can talking about the components now. So we have F1 now, we have F2 now, right? So then what is relationship? Angle is theta. You can find we have a relationship here, since the original force is F1. So we have F1 equal to capital F1 cos theta and F2 equal to capital F1 sin theta. So these are the components, right? Okay. So similar thing is here at this end, and we can say here you have F2, and then there are 2 components. So this is F3 and F4, and you can also write here as well F3 is equal to F2 cos theta, and F4 is equal to F2 sin theta. Yeah, it's just okay. So whatever is valid here, same thing valid, it will be valid here, because you have the same angle. Here also you have the same angle theta. Okay, angle theta, angle theta. Okay. So this is how you, in this case F1 is given, and hence you can find out the components. Similarly, given the component, you can also find out what is the force in this direction. So inverse of that. So you can write, we can write here like this, sum it up as F1, F2, F3, F4 is equal to, okay, so F1 will be capital F1 cos theta. So let's put it here F1 and F2 only, like here, and we have F1 and F2 here, like this one. So F1 cos theta, and then we will have F2 times 0, right? That's what we will get, we should get. Yeah. So we have F1 cos theta, and F2 we have multiplication with 0, so we will have this. So we get a small f1, capital F1 multiplied by cos theta, that's it, and F2 multiplied by 0, so hence 0. So F1 cos theta, a small f1 equal to. Similarly, you have F2 equal to capital F1 sin theta, so you can have sin theta 0. Similarly, you have F3, F2 cos theta, so should be 0 here, cos theta here. So let's expand it like this. So you have 0, you have cos theta, then you have 0, you have sin theta, like this. Okay, so this is the relationship you have. Okay. You can also find out the inverse relationship. Yeah, so just to see how they are related. So instead of let's say you are given the F1 and the F1, F2. If you are given F1 and F2 and you have to reconstruct F1, how will you find out? So what we want to find out is now other way around. So you have F1, F2, and here we have F3, F4, and we are going to relate with what? We have F1 here, we have F2 here. Okay, now equation, same kind of equation we can write here as well. And what is the relationship? We have F1, this capital F1 is equal to F1 cos theta plus a small f2 sin theta. Okay. What is the value here? What is the value here? Value here will be 0. As we know that this is a truss system, there is no force which will be there is no force which will be perpendicular to this one. Basically what we mean is at the joint it can have force in any direction, but the force that it takes, hence the force through this bar, is always along the length only. And since we are talking about the bar only, we are not talking about the combined force due to any other member which will be here. We are just talking about this only, hence the force will be along this bar only. And this F1 is the force through this bar only, yeah, at this point. Now, if we look at here, since there is force in this direction only, there is no force perpendicular to this one, we can also write equation for that. What will be that equation? 0 should be equal to F1, and we are taking the components perpendicular to the axis of the bar should be 0, right. So we have the component of this force along the axis of this force and that force both added together should be equal to F1, and otherwise this force component of this force F1 perpendicular to the axis plus components of F2 perpendicular to the axis should be equal to 0, and hence we have F1 and then we have theta plus 90 degree from here, right. So perpendicular to the axis we are talking about. Yeah, so F1 cos pi over 2 plus theta, right, plus F2 cos, okay. So from here to here we have theta, here to here 90 minus theta, and we are taking component here, and hence we will have from here to here we will have theta degree. So theta 90 minus theta here, right. So we have cos theta simply. Yeah, so or we can write 0 equal to, and this is nothing but minus sin theta. So minus F1 sin theta plus F2 cos theta. You can see that it has to be minus, because if this is a cos theta component of this one in this direction becomes F1 cos theta, perpendicular to this one in this direction becomes F1 sin theta, hence in this direction it will be minus F1 sin theta, and hence it is coming here, and then F2 cos theta, this is theta here. So of course the component of this perpendicular to the axis of the bar will be F1 cos theta, and hence you have F2 cos theta, hence you have this. Similarly, similar analysis you can do at this point, and we can straightaway we can write F2 is equal to F3 cos theta plus F4 sin theta, and 0 is equal to minus F3 sin theta plus F4 cos theta. Yeah. Okay, and why we did? So that we can get some kind of transformation matrix. So we know that if you write F1 0, F2 0, this is you can relate it with the F1 0, F2 0, right. So the idea was to get this one, yeah, get this one, so that you can relate with F1, F2, F3, F4. From here we are going to relate. Okay, so here we can write simply based on this one. So we can write like this. F1 0, F2 0 is equal to, and we are going to write here so whatever the value here will be, let's call it transformation matrix R, let's call it R, and then there will be some, here we are going to write a small f1, a small f2, a small f3, a small f4. The idea is to find out this R. Okay, and this R will be given by, that we are going to find out how. So we have terms will be f1, so it will be, for here start with this one, f1 times cos theta, we will have cos theta. f2 times sin theta, we will have sin theta, right? And then nothing else. So for this one we have cos theta, sin theta, 0, 0. Second term, second thing is we have minus f1 sin theta plus f2. The second one will be minus sin theta, then we will have cos theta, then 0, 0. Similarly, the third one will be 0, 0, cos theta, sin theta, and fourth one will be 0, 0, minus sin theta, cos theta. Yeah, so I am going to write R directly. So we say where this R is equal to, as I explained, will be cos theta, sin theta, 0, 0, then minus sin theta, cos theta, 0, 0, then 0, 0, cos theta, sin theta, 0, 0, minus sin theta, cos theta. Okay. So this is what the R is, where this relationship exists, f1 0, f2 0 equal to this transformation matrix R multiplied by this one. So we are relating the axial force to the forces along the degree of freedom. Yeah, so 1D system to 2D system we are actually relating. That's what it is. Where forces F1 and F2 are corresponding to the 1D forces, and a small f is corresponding to the 2D forces. If this is true, same analysis you can do for the velocity, because velocity and the force both correspond to each other, meaning that if you apply a force this way, there will be displacement in this way, and hence component of this displacement will be towards both the direction. And since this displacement is also a vector, you can do the similar analysis, and hence we can write this for the displacement as well, or we can write actually u1 0, u2 0 is equal to R. This R we are talking about. Yeah, so R matrix multiplied by u1 0 u1 u2 u3 u4. Okay. So we have this already. Now maybe I write R as within curly bracket, so that it's more consistent. So I am writing R within curly bracket. So this becomes equal to this, and we have this relationship. Okay, the next is how to relate with there are two case system, right? So we have one, if we look at this is the K which has been derived from the 1D system. So not to forget, we should relate with what we know already. So what we have done so far is we had a bar element, and we have degree of freedom, this F1, U1 and U2 corresponding forces F1, F2. So U1 and U2, our relationship here is simply F1, F2 is equal to EA over L, and 1 minus 1 minus 1 1, and then you have U1 U2. Then what did we do? We actually same bar let me draw in different color. So we have the same bar, but we are writing differently. I mean, for we are writing in terms of 4 degree of freedom system. So we have u1 and we have 0, then you have u2 and we have 0, and similarly the forces u1 f1 and then we have 0 0 and u2 f2 and we have 0 0 system. Yeah. So u1 f1 in this direction there is a 0 forces and displacement in perpendicular to the axis, and here the same thing. So basically same thing, but here explicitly saying that there is no force perpendicular to the axis. And in this case our system is like this. We have f1 0, f2 0 is equal to EA over L, and then you have 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0, and then we have u1 0 u2 0, right. So this system 1 degree of freedom per node, this system 2 degree of freedom per node, but orientation exactly the same as the previous one. Now this is a transformation, we are transforming basically. So from this we have transformed to this one, and from here we want to transform to something different, and which one? This system where we have a bar, and but this is now inclined at an angle theta. Yeah. And for that system our equations, so here we have a small u1, a small f1, a small u2 f2 and u3 f3 u4 f4. Okay, so we are interested in this system, and for that we want to find out some new k. Okay, and that new k will be something like this. Relation should be something like this. New system we have f1 f2 f3 f4 is equal to, we have some k here that we have to find out, and then there will be u1 u2 u3 u4. That's what we have to find out. Okay. Now here we can use this relationship. We already have this. We have this relationship, then we have one relation, that the relationship between this one and a small f1 f2 f3 f4, that also we have in terms of transformation matrix R. So we have this equation, right. So we have this equation and we have this equation. So let's number it. Yeah. So let's call this equation as number 1. Okay, then we have this equation, let's call number 2. Okay, then we have this equation as well, right. Let's call number 3. Now we are going to sum them up. Okay, so from 1 to 3 what do we get? So, and this is number 4, this is number 4. Okay, so so we are going to put 1 to 3 relations 1 to 3 in number 4. Okay. So so let's see. We have to find out, this value, right? Okay. Okay, so in fact, we will start from this equation. So we have this equation. Just a minute. So yeah, so we have this equation, yeah, old equation. So let's start with number 3. So we are going to start with number 3. So from 3, and from 3 what we have? We have this equation, yeah. However, we also have f1, and this vector also defined in terms of equation number 1. So you will put 1 and 2 in equation 3. Okay. So from let's write here, instead of from, by, okay, by putting 1 and 2 in 3. Okay. So what will we get? So let's see the 3 here. Instead of writing f10 f20, we will write r f1. Instead of writing this one, we will write this r f1 f2 f3 f4. That's what I mean, right? So that's what we are going to write. So we write r, capital R, and then we have f1 f2 f3 f4, okay, is equal to, we have EA over L, and then after that we have 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0, right? And then here also, instead of writing, if you see in equation 3, we have, so far we have completed this one. Even we have u1 0 u2 0. Instead of writing this one, we are going to use this relation. So we will write, instead of writing this one, we will write this r u1 u2 u3 u4. Okay, so sorry. So here we will write r, and then we will write u1 u2 u3 u4. Okay, so we have to find out this big K, and you see we are getting something closer. So if you compare this one and this one, what we have is force vector, we have force vector, we have displacement vector right here. Now we have something here, but we also have some extra thing here. Okay, so we have to do something about this one. Okay, so what we can do now? Basically, we can have R inverse. If it goes here, if you have R inverse, automatically we can find out this one. Yeah. Okay, so R inverse of that, in fact, R is a square matrix. So we can see here, this is R a square matrix. Yeah, so it can easily be inverted. So we can write like that, or we can also try just transpose it, and if you transpose this one, then uh, also we should be able to get something, meaning that we will try if we have R transpose here and R transpose here, whether R transpose R will make it identity matrix or not. I am arguing that maybe, okay, maybe we have to check, maybe R inverse equal to R transpose. If that is the case, then we can get R equal this equal to R transpose here and this value and this. As such, right now this equation we can easily write like this one. We will check later whether this is true, but for the time being, given this equation, we can write as F1, F2, F3, F4 is equal to R inverse, right. So, we have R inverse here, then EA like this one, EA over L, and you have 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0, right, and then you have R again here, and then we have U1, U2, U3, U4, right, and hence we get the big K, this K we are talking about, right. So, this K, the big K, hence we can find out from here that big K is equal to nothing but R inverse EA over L, and then 1 0 minus 1 0 0 0 0 0 minus 1 0 plus then 1 0 0 0 0 0, and then transformation matrix here as well. So, we have found the stiffness matrix, this one, which will be equal to like this one. So, inverse of transformation matrix A over L and this and this. Remember that this will be exactly the same one, should be exactly the same as what we derived yesterday. 4 by 4 matrix we will get based on this one. Now, let us find out whether this is true. If that is true, if R inverse equal to RT is true, then we should get say then RT R equal to identity matrix. Yeah, so we can check that. So, R transpose R, okay, will be equal to R. Let us have R transpose. So, R transpose, if you see the expression for R, which is given here, we have cos theta sin theta 0 0 minus sin theta cos theta 0 0. So, transpose of that, so we get cos theta sin theta 0 0 minus sin theta cos theta 0 0 and so on, right. So, cos theta sin theta 0 0 so we write cos theta sin theta 0 0 minus sin theta cos theta 0 0, then 0 0 cos theta sin theta 0 0, right. Then we have minus sin theta cos theta. Yeah. Okay. So this we have to multiply by cos theta sin theta 0 0 minus sin theta cos theta 0 0 0 0 cos theta sin theta 0 0 minus sin theta cos theta. So we can check also. So the row becomes column, column becomes row. So let's go row by. So cos theta minus sin theta 0 0 cos theta. So we will start with row wise this one. So cos theta sin theta 0 0 cos theta sin theta 0 0 minus sin theta cos theta 0 0 minus sin theta cos theta 0 0 0 0 cos theta sin theta 0 0 cos theta sin theta 0 0 minus sin theta cos theta 0 0 minus sin theta cos theta. Hence this we can write whatever the value is. So let's find out what the value is. So we start with column by we start with one by one. So cos theta and this we are going to multiply it and write the value. So 1 1 will be row number 1 column number 1. So cos square theta plus sin square theta equal to cos square theta plus sin square theta plus 0 equal to 1. So we have 1. Next, this and this, cos theta sin theta minus sin theta cos theta plus 0, actually that is equal to 0 only. Similarly, multiply this, cos theta 0, cos theta multiplied by 0, sin theta multiplied by 0, 0 multiplied by cos theta, sin theta multiplied by 0. So hence we will have 0 value again. Similarly, we can have this multiplied by this. So cos theta multiplied by 0 0 minus sin theta multiplied by 0 is 0, 0 multiplied by sin theta is 0, 0 multiplied by cos theta is 0. So we have 0. Yeah. Okay. Remember we have the two matrix which is not symmetric, but we are multiplying them by transpose, so that makes it symmetric. We can actually you can also see after we calculate we can also find out. Now let's go to the second one. So we have this multiplied by this one. So this, so sin theta cos theta cos multiply plus cos theta multiply minus sin theta. So this multiplied by this plus this multiplied by this becomes 0. All others are 0, 0 by 0. So hence we have 0. Okay, so now we have second here and this one. So sin square theta plus cos square theta plus 0 equal to 1. Sin square theta plus cos square theta. So we have 1. And similarly you can multiply others. So we can see here the number 2 and number 3 here. So 0 plus 0 plus 0 plus 0. So we have 0. And similarly we can have number 2 here, number 4. So 0, 0, 0, 0. So all zeros. Yeah. And so on. Okay, so I am going to write now instead of multiply all. You will see that what you find is 0, 0, 1, 0 and 0, 0, 0, 1. So you get identity matrix basically. So just write I. So indeed we have equal to R inverse R basically, because this identity matrix, this relation is true. If I is identity matrix, means only 1 at the diagonal and all other zeros, then you can also get this by multiplying inverse of a matrix to a that matrix, right. So this is also true. Okay, so what we got is basically indeed this is like that. So basically we can, instead of writing R inverse, we can also write R transpose, and hence our matrix, big matrix K, becomes equal to R transpose EA over L, right, and then 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0, and then we have R here, where R matrix given by, you have to remember this is will be cos theta sin theta 0 0 minus sin theta cos theta 0 0 0 0 cos theta sin theta 0 0 minus sin theta cos theta. So this is what. Okay, so this is, if you actually if you put these values here, if you put this here, transpose and keep it here, and then put this value here, you will get the values exactly same as what you got last time. Okay, so what you will get is like this one. So big K will be equal to EA over L. After multiplying all, you will get, if you remember, you get here cos square theta, then you had got sin theta cos theta, then you had minus cos square theta, and then you had minus sin theta cos theta. Okay. Next is this has to be symmetric, remember, so we can actually copy directly. So we have sin theta cos theta minus cos square theta, then minus sin theta cos theta. Okay. Next here we will have sin square theta. So we have sin square theta, and then remember this and the whatever you have here, the third one should be the negative of the first one, right. This is the force balance we did. Just to remember, I am telling you how to memorize it, so very easy basically. So hence if you have this value, has to be minus sign here, this value you have minus of this. So we can write minus sin theta cos theta, minus sin square theta. Okay, and this is symmetric also, so whatever you got here you can write it here, whatever you get here write it here. Yeah, so minus sin theta cos theta minus sin square theta. Okay, so now whatever you get here should be minus of this here, minus of this here. So you can write here cos square theta and then here sin theta cos theta. Okay, and since this is symmetric, so this value will be the same here. So or you can also write think terms of, if this is minus sin theta cos theta first term, so third term should be sin theta cos theta, and similarly this should be here sin square theta. Right, so we have sin theta cos theta and then we have sin square theta. So this is what the you will get after you multiply this. You know, if you put R value here, means transpose of this will be here, EA this matrix multiplied by R matrix here. If you do this, what you will get exactly the same thing what we learned earlier. Still it was worth working out the derivation, because in computer you have this kind of technique only. So here yeah, basically not this is now derived from the different method, but you have different perspective here. So you have used the rotation matrix. The rotation matrix is the one which is used. Yeah, and there you, in the previous case, in the last video lecture, you had just this value directly derived, but in this case you have in terms of your rotation matrix. So if you have rotation matrix, you just multiply and you can do it. Also here you have the forces, also the relationship between the forces and the displacements as well. So what I mean to say is from here you also know how the displacements are related, means the local displacement and global displacement. Local meaning that we are just thinking about the only 1 degree of freedom per node. From this system, if you know the R, they are related. Yeah, so meaning that if U1, U2, U3, U4 is given, and if you want to find out say stress, let us say if you want to find out the stress or a strain, how will you find out? Okay, so a strain, in order to find out the strain, you always have to know U1 only, right? U1, U2 you have to find out, and hence it is convenient to actually know this relationship, and accordingly we can find out. So let's even find out here. So if you have a strain will be equal to U2 minus U1 divided by L, right? This means what is the displacement divided by L is the strain, right? And if you that really means, what it means is you can write in terms of so 1 over L, and then you have minus 1, and then you have a displacement U1 and U2, right? Okay, but if you have let's say you don't know, you have formulated and you don't know what is U1 and U2 is. What you know is U1, U2. So I would say you know u1, u2, u3, u4 and don't know u1, u2. Okay, so then how will you formulate? How to find out the strain then? How will you find out the strain? So in order to know the strain, we have to use that relationship. So a strain is equal to, from this one we can expand even further. We can say this equal to 1 over L, and then you have minus 1 0 1 0, and then you have u1 0 u2 0, right. This is also true. And once you have this, then we can also have is equal to minus 1 over L, and then you have minus 1 0 1 0, and then this is nothing but the R. Now R comes into picture. R times the R times the, I am writing the this one u1, u2, u3, u4 transpose I am writing, right. So that really means what identity I have used, this one is equal to R times this one. So we can see that like in one of those. So here one more here, yeah. So you have u1 0 u2 0 is equal to R times this one. So I am using this identity. So if you know this, you can find out this, and if you have this one, you can find out the strain and even a stress as well, yeah. So this is the advantage basically. In the earlier case we had the forces and all those things, but in order to calculate a stress or a strain, you have to, it is not direct. You can calculate it still, but it is not direct. Here it is directly. Once you have this u1, u2, u3, u4 multiplied by transformation matrix, that will convert into this one, this multiplied by this will give you a strain, and a stress also you can find out. Stress equal to nothing but E times epsilon, and so a stress, if you know the strain, you know the stress, sigma equal to E times this. So you can calculate the strain by this method multiplied by the Young's modulus, you get the stress, yeah. So this is very convenient to actually work like this one. Okay, so that is all, and we have finished chapter 1 now. So please solve the exercise problems, okay. And then we can, if you have any problem, we can talk about during the live sessions.